Good morning, everyone. My name is Dushanshu Pandey. I'm a senior executive member of Space Technology Student Society, and I warmly welcome you all to today's webinar on space science exploration using balloons as suborbital platform. We are truly honored to have with us Professor Devendra Ojha, Senior Professor in Department of Astronomy and Astrophysics at TIFR and a chairperson of the TIFR Balloon Facility Committee. Professor Ojha is recognized as one of the few researchers whose research span in diverse and critical areas of astronomy, such as interstellar medium, galactic structure, and astronomical instruments, particularly in balloon-borne and space-borne payloads. Under his leadership, the TFR balloon facilities have achieved remarkable milestones, including near space experiments like recent flights of capsule carrying lab rats in collaboration with Singapore. So, sir, we are truly delighted to have you here.
Yeah, thank you very much, Tushar, for inviting me to give this lecture. So let me just share my slide. Can you see the slide?
Yes, sir, we can.
And it's moving, correct?
Yes, sir.
Okay. Thank you once again. Today I'm basically talking about, I think many of the participants here may not be knowing about these balloons. Actually, we have a very unique facility in India under TIFR, which actually does a lot of space science exploration for space agencies, astronomy, climate sciences, and so on. So today I will just touch upon what kind of exploration you can do with balloons, which can be used as a suborbital platforms. So this is the brief outline of my talk. So I will try to introduce you about what is the scientific ballooning and why the role of TIFR National Balloon Facility at Hyderabad, it is located in Hyderabad, is very important for the scientific ballooning. And where can use the scientific balloonings? I mean, it is a multiple disciplines now. Actually, you can use these balloons from astronomy to climate science to even for a commercial application and so on. So I will give you a few examples of these balloons and which direction now we are going with balloons. If you see worldwide, there are a lot of experiments are now planned with balloons, particularly recently, space tourism has become one of the very important aspect where actually balloons can be used. So I will also give show some example of that. So before that, I'm just showing you this electromagnetic spectrum, where the basically the x-axis is shown in the increasing frequency range, and top of that is basically one can go from the uh, low energy to high energy, from right to left to right. And if you see that Earth, basically atmosphere is not transparent in all the electromagnetic spectrum, particularly only the Earth is transparent in the radio wavelength, and there are few windows which are transparent in IR and optical region, which we can view from our naked eye. But if you go to other part of the electromagnetic spectrum like X-rays or gamma rays, in higher energies, you see that Earth is not transparent. That's why you have to go above the Earth atmosphere to do your science exploration, in particularly in astronomy. And the tools to do this exploration is either you send your satellites or rockets or aeroplane or balloons. And we know that sending satellite is it's a one-time investment, means it's not a cheaper tool. So really balloon play very vital role when you are doing this space exploration in these kind of electromagnetic range like high energies or longer frequency ranges. So that's why balloons have become very popular. So, but there are some problem with the balloons that you cannot do this balloon experiment all over the Earth atmosphere. So I just want to show you here. Uh, basically the Earth atmosphere, different layers of the Earth atmosphere. So when you go in higher altitude, first you encounter with the layer called troposphere, and the next layer is the stratosphere and then mesosphere. And particularly this troposphere is basically up to 10 to 15 kilometer of altitude. Then up to 15 beyond that is stratosphere, which is up to 50 kilometer. And then you have mesosphere and so on. And if you see the when you go above the altitude, suddenly you see that when you go to the troposphere, suddenly the temperature decreases very rapidly. And actually you encounter the temperature of minus 80 degrees centigrade or minus 90 degrees centigrade when you are at the peak of the troposphere. And when you just make a transition to the stratosphere, then there is sudden basically temperature inversion, and then temperature becomes minus 40 and 50 degrees centigrade. So therefore, at this temperature and the low pressure, which is roughly like 10 millibar, balloons are the ideal platforms, because if you are in the troposphere, then it's very cold, and generally these balloons are made of plastic material. I will come to that. I will explain that. And they really become brittle, and there is a chance of balloon burst at that altitude. So the ideal plate layers where you can do the balloon experiment is called stratosphere. That's why in general, if you see in literature, these balloons are called stratosphere balloons, because that is the reason where you can do the balloon experiment for space exploration. So now question is that why do we do ballooning? Of course, balloon can play complementary roles to the satellites, because satellites you can actually launch once, I mean, in few years, but balloons can actually do the in situ measurements. And one of the very important aspect of balloon experiment in climate science or atmospheric science is that balloons, when they are launched from the grounds, they have a low ascent rate. So in that case, you can actually have very high vertical resolution of the Earth atmosphere with the balloons using your instrument, which you are actually using as a payload with the balloons. So it can actually give you high vertical resolution, and actually that actually helps you to study very deeply the Earth atmosphere and particularly the monsoon dynamics and so on. In other case, if you are launching the rocket and satellite, they go very fast. Their ascent rate is very fast. So you cannot get really high vertical resolution of the Earth atmosphere, which is very important in the troposphere range up to 10 kilometer and so on. So therefore, these are very important balloons for this climate science studies. And of course, balloons are low cost. They have a quick response method. You can launch balloons and recover your payload and launch it again. Unlike satellite, you can launch only once and there is no control. And also you can do a lot of in situ measurements of the balloons. You don't have to confine in one location. You can have a mobile experiment anywhere. You can take balloons and launch them. So that can give you the in situ measurements. So these are the main advantages with balloon as compared to the satellite. So now I will give you briefly about the history of scientific ballooning in India. But just before that, let me talk about what was the historical background of these balloons. So actually this evolution of balloon design actually was almost 2.5 centuries ago, were basically discovered by two French brothers called Montgolfier brothers. So what they did is in 1784, they actually used this varnished silk back as a balloon, and they actually launched these balloons to that stratosphere almost like 240 years ago in France. And that was the beginning of balloon experiment. And later on in 1930, people started using the fabric kind of envelope with rubbers, and these were used to launch, but these balloons were only going up to 20 to 40 kilometer, 20 to 24 kilometer, and then they were not able to sustain, and they generally got burst at that altitude. And then in 1950, actually the plastic balloons were developed, which has an integral load tape. I will explain you the next slide. And these are become called natural shape balloons, and which are actually now, till now, we are using these natural shape balloons for space explorations. So one of the very important discovery which happened in early 90s was discovery of cosmic rays by Victor Hess. And this was actually, these experiments were done with balloons, and Victor Hess subsequently in 1936 received a Nobel Prize for that discovery. And then the stratospheric flights were started in 1930s, but they were reaching only 20 kilometers around the tropopause. But in 1950s, that was the discovery of natural shape balloons by German technical guy called Otto Wingen, who actually presented the modern day natural shape balloons. And these balloons are actually made of plastic or polythene material with their integrated load tape, which can carry heavy payloads up to 30 kilometer or beyond that. And since then, of course, there is a lot of R&D work on then balloons, and these plastic balloons have become very important stratospheric balloons for space exploration. In India, scientific ballooning was started by Dr. Homi Jahangir Bhabha, who was the founding director of TIFR in late 1940s. However, Dr. Bhabha was using only the rubber balloon, cluster of balloons from different part of India. And the major goal of this experiment was to study the secondary cosmic rays radiation in the Earth atmosphere. And actually, Dr. Bhabha used these clustered rubber balloons from different part of India, all over India. And they had done a lot of new discoveries of the secondary cosmic radiations. And this experiment was actually conducted till 1955. And then Indian Balloon Group actually started development of plastic balloons technology in 1956 in TIFR. And the first successful balloon flight took in 1959 from Mumbai. That was with the actual natural shape balloon. So that was kind of a scientific ballooning beginning of experiment in India. So just to give you some background of what are these balloons. So the major constituent of these balloons are basically the polythene film or plastic film, which are actually the processed film. There are a lot of chemical reagents are used to process, extrude this film, and so that they can sustain this very notorious environment of troposphere. So basically, you can make these balloons by cutting the plastic in a different sections, which we call as gore. So you can see here different section of this plastic material. And then you can, each of these sections, you can stitch by this load tape. And these load tapes are actually basically nothing but made from polyester yarn, which has a very high breaking strength. Basically, you can combine this lot of polyester yarn and then made a load tape, and then you stitch these different section of plastic, these load tapes. So idea here is that when you are flying a balloon, basically the polythene material takes the shape of the balloon or volume of the balloon, whereas these load tapes are actually taking all the load or payload, whatever you are suspending below the balloon, and they basically carry all the load. So that's why these load tapes are used. Then we use a lot of other accessories in the balloon like top and fitting. And then you have a venting duct. Basically, if you are flying in some altitude and if you want to escape the gas which you are using in the balloons, you can actually use the duct to escape the balloon and keep the same altitude. Otherwise, you will be up and down depending on day and night. So that it's very important that you keep the same altitude of the balloon. And then there are many other devices are used. So it's a lot of R&D work is done in these balloons. I will show you some of the pictures of balloons in later in my slides. So just to continue of scientific ballooning in India, particularly the space astronomy has a rapid success in India, mainly because of the balloon in the beginning. And this was happened because we had a parallel program called Research and Development of Polythene Balloons for High Altitude Studies. These were the dedicated program in TIFR. And you can see in the left picture here, that time that Prime Minister Pandit Nehru is basically talking to the Bhabha to set up this facility in the basement of TIFR. And in the right, you can see these balloons were actually basically made in TIFR. And that was the development of zero pressure balloon in India. But these balloons were that time made from the black polythene film. And the idea was that generally this polythene material were painted by the black paint so that they can actually you can fly these balloons during the daytime. Because when you are going above the altitude, as you can see, temperature and pressure decreases. And so that if you have to keep your balloon uh, uh, really hot or heated condition, you basically paint with the black thing so that when you are flying in the daytime, because of the sunlight, these are basically remain heated so that they can go above the atmosphere. However, you cannot fly these black fill polythene balloons during the night time because temperature is very low, and then balloon cannot absorb the heat and you cannot. So that was the, of course, beginning. But later on, after 1960s and so on, actually the actual balloons with the white film were made, which you see in the right picture here. And these are the balloons which are now frequently used in India, as well as our own balloons are used in the abroad. And these are basically called stratospheric balloons or natural cell balloon made with the white polythene film. Of course, other than other places also, a lot of experiment has started. So as I explained you that Bhava started cosmic ray experiment in India, but then later on TIFR jumped into the X-ray astronomy experiment with balloons, and also Physical Research Laboratory in Ahmedabad, PRL, started gamma ray astronomy experiment with balloons in early 60s and so on. And you can see in left picture, Dr. Kasturi Rangan, who was the chairman of ISRO. He was earlier in PRL, who actually started this gamma ray experiment and X-ray experiment in PRL2. And so then we had a lot of experiment in X-ray, gamma rays, and in later on in early 70s, we actually move into the infrared astronomy experiment. Whereas X-ray and gamma ray, there are no difficulties, but however, in infrared experiment, detectors are very sensitive. Particularly, you have to cool the detector, so that experiment became a little bit complicated. But nevertheless, that's why that beginning started much later compared to the X-ray and gamma ray astronomy experiment. So considering all this, in early 90s, early 60s and 70s, basically TIFR decided to set up a dedicated national facilities in India at Hyderabad. The idea, and this facilities was established in 1969. And the idea was that that facility has to be close to the equator. So as you can see in here, lower picture, that Hyderabad is just 90° north of geomagnetic equator. And idea was that when you are doing a high energy experiment, there are a lot of uh, charge particle, background charge particle, which can actually interfere with your actual radiation, which you are detecting from the celestial sources. So if you are at the equator, you can actually reduce this charge particle background so that you can have more photon from your celestial sources. So that was the idea to set up this facility in Hyderabad. And now this facility is unique in the world. Unique in the sense that it has every ingredients of balloon thing under one roof, because it can actually, we can make a balloon, we have a production unit, we can launch balloon, we can collect data, and we can actually recover the balloon. So there nowhere in the world we have such a unique facilities, and we can actually make a very large zero pressure balloons. And these large zero pressure balloon actually can, we have two seasons which are called summer and winter season, where we can actually do the experiment with a very large zero pressure balloon. I will explain what do we mean by large. However, now throughout the year, we are doing balloon experiment. Particularly many atmospheric and climate science experiments are actually conducted during the active monsoon period to understand the monsoon dynamics, pattern of the monsoon, and so on. So these balloons are right now used for astronomy, astrobiology, climate science, as well as commercial applications from India, as well as our own balloons are used by foreign participants from there, and they are flying from balloon. So as I said, it's a unique facilities, which is shown in this view graph, where we have a balloon design and fabrication unit, which has done a lot of R&D activities for last 50 years. Then we have a control instrumentation and balloon augmentation. These are the electronics division, where basically we use the radio communications to control the payload and gondola, which are used with the balloon. Then we can also have workshop and launch support. So we can actually design the experiment for students or experimental who come to balloon facilities. And then we also doing a lot of climate science research now, because that is there's a lot of demand for basically to understand the mitigation of climate and many other atmospheric science experiments. So everything is under one roof, and this is a unique platform for student exploration as well as scientists who are coming for various experiments. So this is the facilities which is located in Hyderabad. So you can see in this, we have a balloon fabrication where we have a very long table where we actually make a very big balloons. Then we have a launch ground, which is quite, we can actually launch very big balloons. Then we have this radio communication where we are using the S-band antenna, which actually operates at 2 hertz for uplinking and downlinking, from where we can control and get our data through this telemetry. So this balloon is basically, we launch from Hyderabad, which is shown in the center of this box. And we have this corridor, which is actually given by the ATC, Airport Traffic Controller. And these are the requirements from ATC that we can actually fly only this corridor. And this is actually the 500 kilometer across in both directions. And this basically corridors come because of a lot of geographical constraints. Nevertheless, within this corridor, we can actually fly the balloon for almost 4 to 10 hours, depending on the winds at the ceiling altitude. Ceiling means where basically balloon is just floating, where you have a almost zero pressure, differential pressure inside a balloon and outside atmosphere, and balloon just floats there at that altitude based depending on the condition of the wind, upper winds. So if upper winds are very high, then you get 4 hours of experiment, but upper winds are slow, then you can get 10 hours of experiment within that corridor. Of course, if there is no restriction of the corridor, you can actually do these experiments with these zero pressure balloons for almost 40 or 2 days or 3 days without any interruptions. So this is the very important aspect that we control all these balloons, payload and gondola using our S-band telecommand and telemetry. So we have basically operating at 2 different frequencies around 2 gigahertz. So one frequency is used for uplinking, where we send the control. It's almost like a satellite operations, control gondola, send commands and see. And then we have a downlink again at around 2.259 gigahertz, which basically use as a telemetry to collect data, and it operates at 500. We have a basically capability of 500 kbps kind of telemetry we can get. And these are the system which are basically used at the S-band. So that's why it is called S-band telemetry and telemetry system. So let me now show current scientific ballooning activities and recent development which had happened, just to give you some idea or feeling that what kind of experiment we do balloons. So right now there are many research area which we can do with TIFR balloons. Of course, there are experiment in astronomy which we call TIFR experiment, like far infrared astronomy experiment, particularly to look for the star forming regions where new stars are forming, particularly to understand the raw material which are actually used to produce the stars and so on. Then recently we have now started very interesting experiment on quantum communication, particularly the long distance free space optical communication, which for you can do actually like Indian conditions. Balloons are the ideal platform. I will explain you in a couple of slides in a few minutes from now. And then in atmospheric science experiment, we can do many experiments like collecting the atmospheric sample, space biology, mitigation of the climate change, and so on. Then we have a lot of commercial aspect, particularly we can use these balloons for the internet and mobile communication, particularly in the natural disaster conditions. So I will give you actually the Indian government called CDOT has used these balloons to basically use for 5G communications when there is a natural disaster or when you don't have a power and so on. You can use this balloon. And more recently, this space tourism and space exploration has become very interesting, where people are using balloons for sending human to the space and bring them back and so on. So there are multiple applications of these balloons where these balloons can be used. And we can actually fabricate different kinds of balloons. One of our major R&D thing is on zero pressure balloons. These are called zero pressure because at the ceiling altitude, the differential pressure inside balloon and outside is zero. And so that balloon can float and at the same altitude. And this can carry heavy payloads, of course, like 1200 kg up to 32 kilometer. And if this payload weight is like 4,000 kg, then it can go up to 12 or 14 kilometer. Then we have different like sounding balloons. These are used for atmospheric science experiment, but similar balloons are actually used by ISRO before they launch the rockets. Particularly before launching the rocket, they want to study the weather patterns, and for that they basically use this balloon and then they forecast the weather, and then they launch the rocket if weather conditions are favorable. And then we also develop one very interesting balloon called tethered balloons. So these balloons we don't launch. These balloons are actually controlled by the tethers, but they can go only 1 kilometer of height and so on, depending on their weight and so on. Then we also develop many special balloons that is particularly for ISRO experiment like Chandrayaan or Gaganyaan and so on. So these are some examples of balloons. So the first one is actually called zero pressure balloons, which are made of very thin plastic of 12 to 25 micron. And the volume which we can make right now, the biggest balloon is almost like 740,000 cubic meter. It's really the huge balloon which can go up to 30 to 40 kilometer, can carry 2 ton of payload. Then these are the sounding balloon, even much thinner polythene like 5.5 micron, but of small volume like 4,000 cubic meter, but they can go up to 43 kilometer. And these are used for the wind sounding at atmospheric, like ISRO uses, and many climate science scientists are using these balloons. Then we can actually have one high altitude balloon for which we have made a world record. This is almost like 3.88 micron, really thinner, very difficult to handle with the hand. But we have a record of going up to mesosphere, which means around beyond 50 kilometers. Then tethered balloons are basically controlled by the tether so that you can go up to 1 kilometer, and they are made such that they are stable in a high wind condition. So these are called basically the kitoons in other term. And then we have these special balloons made especially for ISRO applications. So just to show you this high altitude balloon, which has a volume of 61,000 cubic meter made with very thin polythene. And as you can see here, we have actually crossed that limit of 51.8 kilometer. But since this is a small, thinner balloon, it can only take a suspended load of 10 kg. So if you have an experiment of 10 kg, then these balloons can be used at 50-kilometer height. And this is kind of a world record because only US and Japanese who has gone to the mesosphere, and we actually has gone with a higher weight. So this is very important achievement for us. Then these tethered balloons are very important if you have to do some experiment to test your electronics or your payload. These balloons can go up to 1 kilometer and you can control from the ground. And why these balloons are very important? Because you can do in situ measurement using these balloons. You can take these balloons anywhere, any location. For example, in the middle panel, you can see these tethered balloons were taken in the Bay of Bengal, and that experiment was done in the Bay of Bengal to understand the monsoon patterns and so on. Then these are some special balloons we are designing for the ISRO applications. And why we call them special? Because as I explained you, as you go above the altitude, when you reach to the troposphere, you can see that temperature suddenly decreases to almost like minus 80 degrees centigrade. And you can imagine if you are using this polythene or plastic material, if you are going at that altitude, it becomes brittle and there is a good chance of balloon burst at that altitude. However, we have done a lot of R&D activities now and actually develop very special balloons which can actually float at around the 16 to 18 kilometer for 2 to 4 hours, where temperature is really minus 80 degree. And this region of the Earth atmosphere is very important because a lot of monsoon dynamics happens in this region, which actually defines the monsoon patterns or weather patterns and so on. And these are some of the special balloons which we have designed. These are called oblate or paraboloid spheroid balloons. And one of the very important application of this balloon is that they can actually use it for the zero gravity test conditions. For example, you can see in the lower panel, actually the Chandrayaan mission, where when they use the rover, they actually check the mobility of this rover in their clean room in ISRO, Bangalore, by using these balloons, because when you are lifting the balloons, it is lift very slowly, so you can actually feel like a zero gravity condition in the lab. So that's why all these balloons, even when they are sending these antennas in GSAT satellite, they actually see the deployment of the satellite and so on using these balloons in the zero gravity condition. So these are very unique applications of balloons. So let me just come to few very important big experiment. These are called TIFR balloon experiment. And one of them is called far infrared astronomy experiment, where I myself is involved. And this is a very big experiment because the total weight of this experiment is almost like 1200 kg. And here we use a telescope, which is a primary diameter of 100 centimeter. And this basically uses in the far infrared range. This telescope has already launched by 27 times since 1983. And we are doing a very unique experiment. Particularly, we are using an instrument with this experiment called Fabry-Perot spectrometer. And this Fabry spectrometer is actually tuned to one of the very important line in the universe at 158 micron. 158 micron falls in the far infrared range. And this line is particularly important because it traces the carbon gas. So of course, we know that most abundant gas in the universe is hydrogen, but it's very difficult to observe directly the hydrogen because of the dipole characteristic of the hydrogen atom. But the next abundant is the carbon gas. So with this unique experiment, we actually observe the carbon gas and then study a very interesting star forming region, which are shown here. So these kind of, basically we generate these kind of maps here, and these are maps basically is the raw material. These are the gas and dust from where we are formed, like sun has formed, or the mass star which are massive, then sun has formed. So with this experiment, we basically try to understand how do we form the star. So we know that of course sun is a star, but still there is a debate that how do you form different masses, different star with different masses. So that's what we study using this experiment. Of course, we do much deeper studies, but that is the layman term. That is what we do. And then this is just to show the scale of this experiment. So basically, this is the main balloon, which has a volume of almost like 150,000 cubic meter. And this balloon is basically tied with this load line here. And then payload is attached at one end on the launch truck. And in between, you see a lot of packages. These are the electronic packages which are used to control the gondola or payload and balloon. And these are basically the telemetry and telecommand packages and so on. And then this balloon is actually filled with the gas. Unfortunately, we are using hydrogen gas, but we have a lot of safety measures. But these balloons can also be used with the helium gas. But as you know that helium gas is very costly. That's why now worldwide people are moving to the hydrogen gas. And just to show you the scale of this experiment is almost like one end to the other. It's like a 200 meter experiment. It's a very huge experiment. And this our payload, far infrared payload, can go up to the height of 32 kilometer, and then it floats around that height. From that, we can actually do a lot of observe this star forming region in our Milky Way and study these regions. Then this is a very interesting experiment on quantum communications, because these can be used, these balloons can be used for a long distance free space quantum key distributions. And that is the need of the hour now, because for security reasons, we have to use this quantum key distribution very soon. Of course, other countries has gone very fast on that. Of course, you can do this from satellite, but one of the problems is that in satellite, when they are moving in the orbit, they actually has a lot of drift when they follow the satellite orbit. Whereas in balloon, if they are launched and if they are at the ceiling altitude, then they have very slow drift there. So the another idea is that if you are using these balloons from the ground, you can cover at a distance, let's say 800 kilometer. But if you can have a tethered balloon and then you launch these stratosphere balloons from this tethered platform, then actually you can cover much larger range, 1200 kilometer. And these are the ideal conditions for a country like India, where you can use this quantum key distribution using these balloons. But of course, these are very challenging because when you are using balloon, you can see that when you are launching balloon, you have random rotations. So a lot of work is done right now in TIFR to basically slow down this rotation, and a lot of decouplers are used and so on. So this experiment is going to be a major experiment in coming years with balloons worldwide. So this is very important. Apart from that, we have a lot of national and international balloon experiment using balloons, and particularly there are a lot of experiment on atmospheric and climate sciences. We have a very important experiment between ISRO, NASA, CNRS, it is the French space agencies, and TIFR balloon facilities. And we are actually studying this basically in India, the monsoon pattern develops when these pollutants come from East Asian countries to India. So basically this experiment is trying to understand these particles called aerosols, or it could be like a black carbon aerosols, which are made pollutants and so on, using this experiment. Then there is an experiment on astrobiology, particularly to search for microorganisms which are coming from other other from so other not from Earth, from other planets and so on. And this again a discussion stage between ISRO, URSC, and some other laboratory in India. Then there are many space biology experiments are done to understand microorganism in cultural medium, particularly to see monitor the growth of different seedling and so on. And these are basically the startup companies who are coming up. This is one of the startup companies in Bangalore who wants to do this experiment using balloons. And then later on, they can actually go for satellite experiment once they understand the technical know-how using balloons. And this is one of the major experiment on climate science, which has been last 10 years we are doing, particularly to measure the physical, chemical, and optical properties of these particles called aerosols in upper tropopause and lower stratosphere region. And this has been very successful because a lot of these results from these experiments were used to predict the monsoons. So particularly the theoreticians have used this data in their computer to predict the climate monsoon pattern and so on. And then there is another experiment from ISRO to understand, and these are basically from rubber balloons. These Batal campaigns were used zero pressure balloons, bigger balloons, but you can do this also from rubber balloons, but your payload weight will be low here, less here. And this is basically to understand the dynamics of this tropical tropopause using various sensors like radio sonde and so on. And then you can also use tethered balloons to understand atmospheric science at altitude of 500 meter to 1 kilometers. And particularly there are experiments from National Physical Laboratory in Delhi. They are actually understanding the vertical profile of aerosols and pollutants in the region of Delhi. This is a very long range experiment, sorry about. And then many East region of Indian countries are using these tethered balloons in their region. So you can see all over India, these balloons are used to understand the weather patterns and collect the data and then predict the monsoon pattern and so on. And another very important application of tethered balloon is communications, which I explained you earlier. And these can actually provide a broadband and communication services, particularly in the rural, remote, and inaccessible areas of country, and particularly in the natural disaster conditions when you don't have power and so on. So you can use these balloons with battery operated instruments and so on, and they can actually use as a last mile communications when you have in earthquakes or floods or landslides and so on. And then you can actually use these balloons for agriculture and horticulture, where you can spray the pesticides and so on. And this is one of the experiments done in TIFR Hyderabad, and many other like imaging and surveillance and so on. So actually, C dot in New Delhi. There's a Government of India establishment who actually use our balloons, and now actually this has become very important. Their major project where they want to basically work on the disaster relief plan using drones and balloons to carry 5G operations. They have already started this prototyping of these 5G operations using balloons and other things, and probably they will use this in different part of India very soon. Now, let me quickly go to the commercial applications. So there are a lot of international interest are there to use our balloons. And particularly one of very important is the space exploration and space tourism, where, as I said, they want to send humans into space and they want to see this edge of the Earth in the stratospheric altitude and then come back to the Earth again. And this has already done a lot of work now in USA, Spain, and so on. And actually, they have tested their capsules, pressurized capsule, where they want to send the humans, and then they are going to send humans. Particularly, US has done that experiment, and Spain is doing it very soon. And then these balloons can also be used for climate change mitigation experiment, like how to reduce, slow the global warming. So there are different methods where you can use these balloons to basically slow the global warming and so on. So these are the prototyping is done by Harvard University and USA, one of the company using our balloons. So these are the pictures where these different experiment were used. And these are some of them are the space capsule, one of are the new development of balloon design and so on. And so one of the important experiment which was done in TIFR Hyderabad was to again one of the Singaporean which they wanted to send the Singaporean in the space, so they tested their capsules with using balloons, and this was done in India, and they were actually using the live animals, rat, deer, to test this experiment. It was quite successful, and based on that successful experiment, actually they validated these capsules from Australia, because in India it's not, I mean, you need a lot of permissions to send humans into space, but since Australia has a lot of desert, so the same guy actually went to Australia and he basically tested his capsule. Basically, the know-how was done in TIFR Hyderabad using live animals, and then same capsule was used in Australia, and they actually created a record of first Singaporean into space. And that was the one of the major experiment. And more recently, the Spanish company called Hello Space, they have tested this capsule from TIFR Hyderabad by sending it to 42-kilometer altitude. And now they are actually doing this experiment from Riyadh, Arab countries, because again, they can do there because there's a big desert there. And then they have a plan next year to send humans to space for space tourism using balloons. They can send 8 humans in one capsule and so on. And then there is a crazy experiments are done in balloons. For example, this is one of the very interesting experiment where one of the Google executive called Alan Ustaz, who used our balloons to make a world record of skydive. So he went up to 41.422 kilometer and he jumped from that height. And this is still the world record of Alan Ustaz. Nobody has broken this world record so far. And this is a very important experiment using our balloon, which of course was done from New Mexico in USA. And this world record is still holds. And then apart from that, we do a lot of student outreach and popularization, student training, just to see some glimpses of that. So we basically organize a student outreach program, invite students from colleges, schools, engineering, as well as students from abroad to do a lot of experiment using tethered balloons or rubber balloons or zero pressure balloons. And based on this experiment, they actually do send their CubeSat in balloon, and then some of them actually propose this experiment with ISRO in the for when there is a launch of satellites. And one of, just to give you one example, this is the experiment done by the student from BITS Pilani, and they actually developed one cosmic ray experiment, and they have a idea was that they wanted to see the impact of cosmic rays on the pilot and the crew members, basically when they are flying the spacecraft. And this was a very successful experiment which was done from they actually developed whole cosmic ray telescope and launched from the balloon facility Hyderabad. And actually, finally, they have patented this experiment. So actually, you can do really very deep and very intensive experiment using balloon. And then once successful, you can actually file the patent and so on. So you can see this details of experiment in this paper, which is in archive. And later on, I think they wanted to propose in on the satellite this experiment. So just to summarize the major achievements so far, we had world record of going to mesosphere beyond 50 kilometer. Then we also had a major milestone in 2018 when we actually launched the 500 zero pressure balloons. Of course, from TIFR Hyderabad, many thousands of balloons have been launched, but zero pressure balloons are the big balloons. So these experiments are the major experiment. So that 500 major experiment was done in 2018. And I would actually recommend some of you that this experiment was actually published in Current Science, which is a popular magazine, and you can actually know about the history of ballooning as well as this experiment in this Current Science magazine. And then another major achievements is that a lot of our balloons were used for lunar mission like Chandrayaan missions, and actually these products were really help for Chandrayaan 3 missions. And you can actually get details in the TIFR webpage about this, what exactly we have contributed in that. So just to summarize milestone, that beginning of scientific ballooning happened in early or late 1940s. Then we have lot of work done in development R&D work of balloons, from rubber latex balloons to plastic balloons. And 1959, we had the first successful zero pressure balloon flight. And then we have established dedicated balloon facility in Hyderabad in 1969. And then we develop our own balloons. So all is the in-house development, the indigenous develop polythene and so on. So since 1990 till now, we have a continuing successful balloon flight, now in a different discipline, not only astronomy, but atmospheric science, climate science. You can see commercial applications and so on. So I have a few short movies. So I will just show you, then I will end my talk, just to show you glimpses of what we do. Uh, so this is one of the experiment which I call far infrared experiment done from balloon facility. So this is the biggest experiment, like it can carry 1200 kg of balloon with a 150,000 cubic meter balloon. So just showing you just just before the launch of this balloon, so that you can see how the balloon are launched from there. So this is the main balloon, which just taken out from the launch gear. And right now you can see that this balloon has half filled gas. And it is now taking all this. This is a parachute here. And this is load line where there are a lot of electronic packages there. And this is the main payload here, which is the far infrared payload. And this payload is taken from the launch track. And this balloon now will take this payload to the altitude of 32 kilometer. And as you see, this is a hard filled gas. So once you reach to the altitude, since pressure is decreasing, actually that internal pressure will increase and balloon will become almost like a football ground. We could become a almost round shape there. And then this is another payload where this Spanish capsule was used, where humans will be sent ultimately. And this is again a big balloon, like 286,000 cubic meter balloon, which bent up to 37 kilometer, beyond even 32 kilometer. And this is the same thing. This is a big balloon. This just launch. And you can see there's a load line here, all electronics packages, and it will carry this capsule is here, which is not seen very clearly, but so this is a very big capsule, which is tested. This is a pressurized capsule, or they wanted to test the environment of this capsule. So this will carry this to 37 kilometer. And now I will just show you this world record of Alan Hustas, which he jumped from 135,000 feet altitude. And so this is a very remarkable experiment which was done by Alan Hustas. So he was taken by our balloon. So now he's coming back by parachute. And now this is just to show you last slide. This is the tethered balloon, which basically you can see this tethered, and you can basically control these kitoons from the ground. So you can basically send through this winch, and it can go up to 1 kilometer, and you can do plenty of experiment in that height using this tethered balloon. So these are kind of made of the natural shape, so that even in adverse wind condition, they are more or less stable. Not perfectly stable, but you can do quite a nice experiment with balloons. So thank you very much for.
Thank you, sir, for the wonderful lecture. Now, I think many people will have some doubts, so we can have some questionnaires. So if
Okay.
anyone have some question, you can raise hand. Yes, Vinamra.
All right. So first of all, thank you for the seminar. I quite liked it. My doubt is a bit simple. Like, I just wanted to know how small can you make the balloon for it to be still, for it to still reach, about 20 to 25 kilometers of height. Like these balloons, they're carrying around tons of payload. And what if you just wanted to uh, carry about, about 10 to 20 kilograms, like small payloads, very small payloads. But what if I just wanted to reach big heights?
Yeah, so we can make quite a small balloon. So we have actually had a custom made balloon called 300 cubic meter, which can carry, I mean, it depends on what is your payload weight. So depending on basically how the balloon which we design is, we consider few parameters. So one of the most important parameter is the payload weight. So if you have, your payload weight, we can custom design that balloon with that particular height you can reach. So we can make a small balloon for no problem. That like 300 cubic meter or something, which are routinely used around 20 to 25 kilometer with less than 10 kg payload or something.
And for how long are these balloons stable in the air? Like at the maximum ceiling height, for how long will they stay there?
Yeah, so that I told you about. So it depends on what is the wind condition at that ceiling
Sorry.
altitude.
Right.
So we have we can actually continue this balloon experiment for 2-3 days, but unfortunately we have given a very fixed corridor. So we cannot cross that corridor. So our basically experience is that you can have an experiment from 4 hours to 10 hours within that corridor.
All right. Yeah. Thank you.
Yes, Piyush.
Hello, am I audible?
Yes, yes.
Yes. So thank you so much for this wonderful lecture. So my question
Thank
is,
you.
how does the shape of the balloon influence the flight dynamics, like the stability and the trajectory of the balloon?
Yeah, so basically in the natural shape balloon, what happened that because you are suspending the payload in the bottom of the balloon, so you need this onion shape kind of inverted onion kind of shape balloon. So so in that condition, what happens that when you are launching the balloon, you are basically ascending the balloon. So you need this natural shape. Okay. However, if you are doing the experiment at the lower altitude, like 1 kilometer, then you need some kind of fan or other kind of like you might have heard the name called aerostat. Okay. So then that can actually try to basically balance the air which is passing through the horizontally to this. So in the natural balloon, say balloon, you have to see because you are going vertically, so you need and there is a weight at the lower, then you need this inverted onion kind of shape. So that way the shapes are defined.
Okay, sir.
Yes, Razan, you can ask your question as well.
Good afternoon, sir. Thank you for that insightful session. I
Thanks.
have basically two questions. The
Mm.
first one is, like in the initial experiment that we did, we used black colored balloons, right? So why did we
Which balloon?
switch over to
Can
the
you
white
repeat
ones?
your? Can you repeat your?
The black colored balloons that we used.
Black color. Okay. Okay. Yeah.
Yes, yes. So why did we switch to the white ones?
No,
And
because
what
we
is the
wanted to
benefit of
experiment.
the
Yeah.
white
No,
ones over
white one
black
because we
ones?
wanted experiment during night. So for example, if you want to do experiment in infrared range, then you have to do in the night. You cannot do in the daytime. Whereas in X-ray and gamma ray experiment, you can do in the daytime also. But when you are doing optical or infrared experiment, you have to do after sunset, okay, because you cannot observe star or star forming region. So idea was that if you want to do experiment in the night time, then you cannot use the black polythene because then these polythenes, the time early in 15 and 16 when you were using bell polythene, they were doing only the daytime experiment because that time there's enough sunlight to make plastic heated so that they can doesn't get burst in the high altitude when temperature is low. But later on, this white polythene were used, but lot of development were done. Lot of new resins, chemical resins were used to make sure that their breaking strength is enough when they were passing through the tropopause. So that was the reason.
Okay, sir. So my second question is that, like as you mentioned in your slides, we use telecommand for the balloon control.
Yes.
So what exactly by balloon control do we mean? Like, can we control the direction in which the balloon is going?
No. So we cannot control the balloon. So what we control is, for example, like my experiment, I have a payload telescope. So I can control the movement of the telescope. Suppose I want to point, let's say, Orion star forming region, and then I want to go some other star forming region. So all this telescope, everything can be controlled. But balloon is can because payload is basically suspended below the balloon, and balloon is just floating as upper wind condition. Whatever upper wind condition that will basically decide the balloon float. So that cannot be controlled. However, you can control balloon when you want to terminate the flight. Okay, so what we do is when we want to terminate the flight, what we do is we have this, you have seen this long load line. In that load line, we have many electronics packages, and one of them is very important package is called squeeb. It's like a bullets, like when you fire the bullet. So what happens that when you fire the bullet, basically it has a long wire connected to the balloon. So what we do is when suppose I decide that at this location I want to cut off my balloon and I want to complete my experiment, then the most important thing is that I have to safely recover the payload. And second condition that when I am terminating a flight, my balloon should not fall on top of the payload. Otherwise, when balloon is coming down, you cannot use parachute. Finally, the parachute brings the telescope down so that you have a safe recovery. Okay. So what we do is when this experiment is decided to be closed, so we just fired the bullet, and this has some rope which basically tears the balloon so that all the gas is taken out the balloon and balloon falls separately and payload comes separately. Okay. And initially the payload has a free fall, but at certain altitude like 10 to 14 kilometer, parachute operates and it brings the balloons down. So that's why this was so that's why these are the controls on the balloon. But however, when experiments are done, actually when observations are going on, there is no control on balloon, but only at the flight time or when there is some emergency, suppose there is some balloon is going in a wrong direction and so on, then we can control by this. We can basically destroy the balloon and so on. So all those radio commands are used here.
Um, any other questions?
Yeah, just one more small doubt. The material had a thickness of around 5 to 20 micrometers. So, like, is there a big risk of tearing at, suppose by some debris that might be flying around in the air? Is there a risk of tearing of the material? Or if there is, then how big
So
is it?
not really, because these plastic are very rigid. I mean, if you have chance to visit Hyderabad, then generally we give this plastic to somebody to just stretch it. You cannot really do it. It's very strong. We use resin such that there is very less chance. Only so generally what happens that most of the means we have to be very careful while balloon making. Once balloons are made, then dust and other cannot really that much do damage unless really you use some nail or something. So these are very rigid material. And another thing is that sometimes we use multiple layers of balloons. So depending on the payload weight, generally double layers are mostly used. So we don't use single layers always. And sometimes triple and four layer balloons are used for a bigger experiment and so on. And of course, when balloons are made, they are made in a very ideal environment where there's no dust, no, it's completely clean and so on. And actually, when these balloons are made, we not even allow people to take their mobile phone or so on. And there are very lot of restrictions when balloons are made. Yeah.
All right, thank you.
So, there was one question from my end as well. So, like you have mentioned, there was a facility in Hyderabad because it's near the equator. So, like, how much that difference makes it going near the equator for these types of researches?
So generally, the near the equator main advantage is for high energy experiment like X-ray or gamma ray, because if you are at the pole and other, then you have lot of charge, cosmic ray particles are coming and so on. Whereas equator, there's a less background. So this is one advantage. Another advantage is that India is in a tropical region and near the equator, so that lot of monsoon studies you can do lot of detailed studies of the tropical region. So in both aspect, it is very important.
Okay, sir. I don't think anyone else have any other doubts, so we can end the session. Thank
Thank
you
you so
very
much.
much, sir, for coming here and giving this beautiful lecture.
Thank you so much. My pleasure. Thank you. Bye.
Thank you everyone for joining. We can end this session now.